an equation governing the flow. Now, I don't know why, but people will not simply do flow into junction equals flow out. I will tell you again, this is how you should do this. So I'm looking at the picture, so there's a junction on the left here. The flow into that is x3 plus 8. That's the flow in. Equals the flow out of that, I see x1 plus 7. Okay. Then up over here, you have another junction. Flow in, I see x1 plus 9. Flow out of that junction, I see x2 plus 7. And flow into the other junction, I see x2 plus 2 equals the flow out of that junction, I see x3 plus 5. Okay. Now what you want to do is get all the, now that's technically fine, but if we're going to be doing Gaussian elimination, we want all the variables on the left and all the constants on the right, so I'm going to do that as well. Because I want a 1 in the top left hand corner, I'm going to get all the variables here on the right hand side. So I'm going to keep the x1 here, and then this one, it doesn't matter. So basically I'm just going to swap these two. So take away the x3 from both sides, you get x1 minus x3 equal to, take away the 7 from both sides, 1. Here take away the x2 and the 9, you get x1 minus x2 is equal to 7 minus 9, which is minus 2. And here take away the x3 and the 2, I get x2 minus x3 is equal to 3. So this answer is part 1, but this is a bit more useful to us in part 2. Write down the linear system governing the flow. We've done that. Part 2, solve the linear system using Gaussian elimination. Back to our Gaussian elimination. So we have 1x, 0x2 minus 1x3 equal to 1. 1x1 minus 1x2, 0x3 is equal to minus 2. And finally 0x1, just going to check this sign here, yeah, looks good. 0, and I could be a bit smarter here as well. So this is a shortcut as well. What I can do is, like here, if I'm going to have a 1 here if I keep going with this. So wouldn't it make more sense to put that in the second row so that the second pivot's sorted? So that's just a clever shortcut. So put this equation in now, 0x, 1x2 minus 1x2 is equal to 3, and then put in this one, 1x1 minus 1x2, 0x3 is equal to minus 2. Okay. So now we've got 2 pivots sorted. Now this is going to get messed up, but let's go. So use this pivot to go at this. We're going to do row 3, send to row 3, take away row 1. So I get 1, 0, minus 1, 1, 0, 1, minus 1, 3. 1 minus 1 is 0. Minus 1 plus 0 is, minus 1 minus 0 is minus 1. 0 minus minus 1 is 1. And minus 2 minus 1 is minus 3. Okay, now you might be noticing something here, but we'll just keep on going. So, we've got, what have we got? We've got pivot, 0, 0, that's good. Pivot, we need to turn this into 0, and what we have to turn this into 0 is to add 1 and take this one here. So I'm going to do row 3 sent to itself plus row 2. So I get 1, 0, minus 1, 1. 0, 1, minus 1, 3. And then the next one, so 0 plus 0 is 0. 1 plus minus 1 is 0. Minus 1 plus 1 is 0. And 3 plus minus 3 is 0. So Are there solutions? Yes, we've seen what no solutions look like when you have zeros and then non-zero, but that isn't like this. So now you look at the pivots. X1 is a pivot, X2 is a pivot, X3 is no pivot, so X3 can be anything, X3 can be a parameter. Okay, so now we can solve for X2. X2 is equal to 3, this is minus X3, add that to both sides, you end up with X2 is equal to 3 minus T, added to both sides is plus T. And then similar story here, X1 is equal to 1, add this to both sides, so 1 plus T. Okay, right. Solve the system using Gauss elimination. To see does this make sense, you can put in those values onto your graph and you'll see, or onto the picture on the page, and it makes a little bit of sense. So if I just do a little bit of it here, because I might need it for the next question actually. So we'll see does this actually make sense when I'm going to do a simplified version of it. So a simplified version of this junction, there's 8 coming in and 7 going out, so a simplified version is there's 1 coming in net. This one net is that there's 2 coming in, because there's 9 coming in and 7 going out, and the other one there's 5 coming out and 2 going in, so a net version would be 3. I don't know if this will help us. X1 then is 1 plus T, X2 is 2 plus T, sorry, 3 plus T, my apologies, and then this is T, and then this should make sense roughly, like everything. Okay, it doesn't explain everything, but it tallies. So you got this, and which way are these going? This is going this way. So there's T flowing here, and there's an extra 1 in, so that's where you're getting the 1 plus T. And an extra 2 is being added to that, so you get 1 plus T plus 2 is 3 plus T. And then this 3 comes out, and then the T continues as it were. Okay, so in terms of have I answered the question that's been asked? Yes. Does my answer make sense? Yes. Now, next question. Given that cars approaching the roundabout must turn left, okay, and the model doesn't include queuing, is it possible that X1, which is this thing, is equal to 7? Okay. I see why not. Well, let's see. Okay, so there's various different ways we could look at this, but probably the easiest is to say, okay, if X1 is equal to 7, what's the value of T? And let's look at all the solutions. So if X1 is equal to 7, it shouldn't be too difficult to see that T is equal to 6. And that means that X2 is equal to 9. Right, now we'll have to draw this picture again. I don't think there's any other way of explaining this. So we get 7 coming out here, 9 coming in here, then X2, which would be 9. This actually looks okay. 5 going out here, 2 going in here, and it says X3 is equal to, which is T, is equal to 6. Okay, I'm not too sure what's going on here. Let's see. 8 in, 7 out, and then this X1 will be 7. Is this possible? No, it's not possible, because if there's 8 cars per unit time coming out here, this will have to be at least 8. So it's not possible that this is 7. So the question would be, what's the answer? Given that cars are probable, just is it possible? Not possible. Because X1 has to be bigger than or equal to 8. Because all these cars coming in have to go left. Okay, that's that. Doesn't make sense. Yeah, it's basically just saying that this couldn't be that small. There's too many cars coming in. It's a different question than to ask which values are possible. But in fairness, I didn't ask that. Okay. Now we're on to question E. So I don't have too much by way of hints here. As I said, there's just Probably the best thing to do would be just look at loads of questions, exercises in chapter 1, or if you want to get it kind of shows that there's not that much pattern to it. Okay, a few things are going to be there, like you're going to have a temperature plate as this question, but maybe looking back at the past exam papers shows that there's /is and isn't a pattern. Okay, what have we got here? We've got a plate in dimensions 4 to 2 and subject to boundary temperatures as shown. Using an appropriate grid, find a linear system whose solution approximates the heat distribution of the plate at internal grid points using the mean value property. Okay, so we've got this plate here. It's in the dimensions of 4 to 2. So 4 across 2 here. And that means you can grid it like this. So that's your 2, and if it's 4, you can go like that. Okay, and it's got some boundary temperatures, 10, 20, 30, 15. 10 all along this face, 20 along this face, 30 along this face, 15 along this face. Heat distribution, so we're interested in, it says heat distribution, that's bad, it should say temperature distribution, but let's do that. So let's call this T1, this temperature T2, and this temperature T3. And the mean value property says that the temperature at any point is equal to the average on the circle around it. Well, how about drawing a circle like this, and rather than taking the infinitely many points, just the 4 adjacent grid points, and that's your linear system whose solution approximates the temperature distribution. So the 4 adjacent to T1 are 20, 10, 15 plus T2 and average those 4 out. We'll do the similar story for T2. You get 20 and 15 and T1 and T3. Find the average of those 4. And finally T3 is equal to 20, 30, 15. And then T2 is also adjacent to it, divided by 4. So that's part 1, write a linear system. So have we answered the question that's asked? An appropriate grid? Yeah, that's an appropriate grid. Find a linear system whose solution approximates. It approximates because we're only using 4 of these points rather than infinitely many. Assume the boundary temperatures of units of degrees Celsius. That doesn't seem too important. Okay. Next thing is starting with an initial temperature. So it gives us a starting temperatures. Basically, these are starting guesses of what the temperature would be if this is in equilibrium of 15, 18, and 22. We may as well write that up here. Use 2 iterations of the Jacobi method. Looks like a vector. So the starting temperatures are 15, 18, 22. So the Jacobi method says bang in the previous temperatures into those equations, and that will give you another approximation that is in a certain sense better than the other one, and that if you keep doing it enough times, the solutions converge to the exact solutions of these equations. Okay, and it's asking for 3 significant figures, no bother. So T1 first, so the first iteration, so I call this temperature 1, first iteration. So these numbers add up to 45, plus the previous T2 is 18 over 4, and we'll round this to 3 significant figures. I get 15.8. If you take more significant figures, obviously that's okay. Second temperature, first iteration, these numbers add up to 35. Previous T1 is 15, previous T3 is 22, all divided by 4, 3 significant figures. I get 18, so no need for the approximation. And then third temperature, first iteration. So these seem to add up to 65, plus previous T2 is 18, divided by 4. Let's see what we get. Three significant figures, 20.8 approximately. Now there's all kind of theory questions that can be asked here. You'll have to go into the exercises in this section to see what they might be. So it says 2 iterations, that's the first iteration. We just have to do this once more. So the second iteration to the first temperature is 45 plus, use this, T2, the previous T2 is 18. Oh, I got 18 twice, okay. So I'll get 15.8 again. Then this one, the second iteration, the second temperature is 35 plus previous T1, previous T3, 15.8, 20.8. So I get 35 plus 15.8 plus 20.8 divided by 4, 3 significant figures. It actually equals 17.9. Not much movement in that, suggesting that it might be accurate. And T2, 3 equals, so the equation is 65 plus the previous T2, which is 18, and that won't change either. So that gives me 20.8. And that's weird that it's actually converged straight away, and that's the reason it's converged straight away. There's 2 reasons. First of all, the initial guess wasn't too far away from the exact solution, and the second is we're only doing 3 significant figures. It would take a bit more if you were trying to get it correct to 4 significant figures. There's no theory question done there. Have we started at the initial temperature? Yes. If we use 2 iterations, 1, 2, have we approximated the solution of this linear system? We have. Have we used 3 significant figures? We have. Does the answer make sense? Have a look at the picture there. Which one should be the hot one? Yeah, T3 on the right. The coldest one should be T1. Everything looks good. Okay.